Okay. So try not to look ahead in the notes. We will use the notes for some example problems, the first one today and then some more tomorrow. But what I want to do today is talk about our new unit. But what we're going to do is use something that we're all very familiar with as a springboard to the new unit. Okay. And that thing that we're going to start with is Newton's second law, which we all know at this point, the net force acting on an object, the net force is a vector, is equal to the mass of the object that force acts on times the acceleration that object experiences as a result of that net force. And then what I'm going to do is just do some algebra on this and restate it in a different way. I'm just going to restate Newton's second law in a different way. The interesting thing is that when you do introductory physics, learn Newton's laws, and then you learn what this new unit will be all about. Newton did it backwards. Newton actually went the other way. Okay, he started with what we're about to start studying, and from that starting point, ended up with Newton's laws. So Newton's laws came from that. Okay, you guys, you don't need your computers open right now. You guys can close your computers. So we do it backwards, and it makes sense. It makes sense if you're developing the actual physics. If you're Isaac Newton, it makes sense to go backwards. But when learning it, it's actually easier to learn it by learning about Newton's laws first and then using those to talk about what we're going to talk about now. So, I'm just going to do some algebra here. I'm going to make some substitutions. First of all, I know, you should know, you need to at this point. If you don't, you're in the wrong class. That acceleration is change in velocity over the time interval over which that velocity changes. Most of the time, you just write t in the uniformly accelerated motion equations, kinematic equations. We just put t instead of delta t, but understand, hopefully you already do, that delta t is just final minus initial time value. But usually we just start our time at time equals 0. And so delta t is simply just t, which is why in the kinematic equations we just put a t there. But for the purposes of today, I'm going to leave it as delta t. Okay? And when I see delta t, Mr. P from Flipping Physics likes calling it change in time. I like thinking of it as just time interval, elapsed time interval. So I'm going to make that substitution in for the acceleration. I'm going to multiply mass times delta v over delta t. Mass is in the numerator. So it's going to be, so whenever I make that substitution, I get net force is going to equal mass times change in velocity over time interval delta t. Delta v is a vector. It's just a vector that indicates the velocity change, right? So delta v is in and of itself a vector, and it's used vector addition to figure out what delta v is, right? You line them up tip to tip. It's just delta v is final minus initial velocity. And so you take the final velocity vector, draw it, and then you take the initial velocity vector, but you flip it, and you add the negative of the initial velocity vector. So, then I'm just going to do some more algebraic manipulations. I'm going to multiply both sides by delta t. And so I get the net force. Why am I doing this? Because I'm allowed to. You can do anything you want to an equation as long as you do it to both sides. You know, most of those things won't help you with accomplish anything worthwhile, but some do. So when I do that, I just get that the net force times the time interval equals the mass times the change in velocity. And then I'm going to use my knowledge that I applied here with my delta t. I'm going to say, well, delta v I know is just final velocity minus initial velocity, v minus v naught. And so I get the net force times the time interval equals mass times, in parentheses, final minus initial velocity. And I could, if I so chose, distribute that m over both terms, and I get the net force. Let me actually write it up here. I get that the net force times the time interval equals mass times final velocity minus mass times initial velocity. Now here's a great time to stop and to just tell you how theoretical physics works. Because there's a big misconception. Some students just see all these formulas and they're just like, they don't understand where they came from. They think that, Einstein just sat around one day and was like on his paper and just like, oh, I bet probably equals mc squared. Right? Yeah, probably. That's not how science works, right? The theoretical work that led to this, and by the way, this is only true if the mass m is not moving. If the mass m is moving, then this equation is actually e squared equals m squared c to the fourth plus momentum squared. But it's not like they just sat around and just come up with that, okay? It's not like someone back in the day was like, I bet kinetic energy is 1/2 mv squared. Or I bet spring potential energy is 1/2 kx squared. It's not like they just said, like the theoretical physics comes first, and then they see these terms. They see these terms like maybe 1/2 mv squared popping up in the equations. 1/2 kx squared popping up in the equations. And then they say, oh, we keep seeing that. That's probably important, so let's give it a name, right? This, I know, has units of kilograms times meters squared per second squared, which is the combination of base units that make up the joule, a unit of energy. So this must be some type of energy. Since it's the energy that an object with mass m has, it's moving at some speed v, let's call that kinetic energy, because kinetic is motion, right? Here, newtons per meter for the spring constant, meters squared, here, gives you the same thing. Kilograms times meters squared per second squared. You get, oh, that's energy too. There's energy associated with a spring that's been stretched or compressed. So let's call that elastic potential energy, stretchy potential energy. Right? We don't talk about equals. You guys know what this means, right? Energy equals mass times the speed of light squared. Yeah. That's how nuclear fusion, nuclear fission works. Right? Whenever you have a uranium or plutonium split into the daughter elements, the mass of that uranium atom, or plutonium, if you're dealing with a larger bomb, the mass of the daughter products is less than the total mass that was there before the decay. That missing mass gets converted to pure, it's not converted, but is liberated in a sense and becomes pure energy in the form of electromagnetic radiation, in the form of heat and exploding stuff. And because the little tiny amount of mass gets multiplied by the speed of light squared, that's a gigantic number. For a little bit of mass, you get a huge amount of energy. That's why nuclear power plants can produce so much energy. One little nuclear power, if you ever learn about how nuclear power plants work, it's actually probably more about this size. Little pellet of your refined uranium about that size will power your house for an entire year. Right? All the heat, all the energy demands for a single house, that for an entire year. Zero greenhouse gases too. It's probably the cleanest type of energy that we can have, which is why it makes me crazy when people rail against nuclear energy. Usually the same people that are against fossil fuels too. It's like, if you don't want fossil fuels, this is the way to do it. This is the way to do it. Yeah, you get nuclear waste issues, but you can just put in Kurt's backyard. Yeah. All right. So the reason I brought that up is because when Newton was doing his work here, he's doing his theoretical work, he kept seeing this type of term pop up. The product of an object's mass and its velocity. Okay. I kept seeing mass times velocity, mass times velocity. Well, kinetic energy, I had a great question last period. Well, can you just say that's kinetic energy, or is it related? It's related to kinetic energy, obviously, but it's not kinetic energy. The units aren't the same. The units for energy are joules. The units for the product of an object's mass and its velocity are not joules, so it's not energy. It's something else. It's something else that's still associated with an object's mass and its velocity, and so Newton came up with a name for that. And what did he call that? You probably could guess at this point.
Force.
No. Force mass times acceleration. If you look at your notes for today, what? Momentum.
Yeah, I knew that.
Momentum. Intuitively, I mean, we've heard the word our whole lives. Intuitively, we know that a large object that's moving fast has a lot of momentum, right? But you can have a small object have a lot of momentum as long as it's just moving super fast. Or you can have a very large object barely moving at all and have a ton of momentum, right? You know those big oil tankers? Those big oil tankers take weeks, sometimes months to go across an ocean. They don't go very fast. They go pretty fast, surprisingly fast. But even when they're just moving like a foot per second, so much momentum because there's so much mass there. And then something like a 50 caliber bullet out of a sniper rifle, you know, the round itself is really big because it's got a ton of gunpowder. But the bullet itself is not very big. But it has a ton of momentum because, yeah, its mass might be small, but its velocity is huge, right? Light has momentum. Light has no mass. So this doesn't work for light. That's quantum mechanics, though. That's way beyond the scope of this class. Yes, light has, but how do we know that light has momentum? Because when light strikes objects, it can give those objects momentum. So we can actually get, you've seen the little things in the bulbs that you put in the sun and then it makes the thing spin, right? That can't happen unless the light particles, the photons of light actually give momentum, mechanical momentum to an object that has mass. But again, that's quantum mechanical momentum because photons do not have mass. So according to classical physics, which is before relativity and quantum mechanics, according to classical physics, light wouldn't have momentum because light doesn't have mass. Mass is zero. So momentum would be zero. But it does, but that's quantum mechanics. That's beyond the scope of this class. So for us, we don't deal with that. For us, we deal with objects with mass that have momentum because they have some speed v. Now, you can have a very large object have zero momentum because it's not moving, right? My momentum right now is zero, or at least with respect to the Earth. My momentum is zero. Okay. So, because momentum starts with the letter P, that is the symbol that we get for momentum. It is a vector. It is a vector. And it is simply defined as the product of the object's mass and its velocity.
Is it uppercase P or lowercase?
Lowercase p. Good question. So that is the equation for momentum. Now, if you guys were in on level, you would get questions like an object is a 10 kilogram object is moving at 2 meters per second. What's the momentum? Right? This class, we will not get questions like that because that's a little too basic. In this class, we get a little more rigorous with it, and so we're gonna have to dig into the physics quite a bit more by noting that m times final velocity is final momentum. N times initial velocity is initial momentum. So I can actually rewrite this guy with our new definition of momentum as net force times the time interval over which that force acts equals final momentum minus initial momentum. Do I have another way of writing final minus initial something? Triangle. Delta. Change it. Right? So final momentum minus initial momentum is change in momentum. And it's going to equal net force times the time interval. Yes. This is how it's written on your formula sheet. You will need to be able to expand it to all these different forms. Okay, so this, note that we started from Newton's second law. That's just Newton's second law rewritten. It's just rewritten Newton's second law in this way. But rewritten in this way, it is called the impulse momentum theorem. You might ask yourself, well, what's the point? Why rewrite Newton's law? Written in this form, there's a lot of very application-driven, a lot of ways, what am I trying to say? A lot of applications that this more readily applies to than just Newton's second law. Okay. And let me just point out one. Bike helmets. If you ride a bike or a motorcycle, you should wear a helmet. Because if you fall and you hit your head on the concrete, you could damage your brain, you can die, right? Notice that if your head comes to a stop, whenever you fall on the ground, your head's going to come to a stop. if it comes into a stop very quickly because it just hits the concrete and stops like almost immediately, or if you're wearing a helmet. It seems like when you watch someone crash, it seems like their head comes to an instantaneous stop, but that's what the padding's for. The padding actually cushions your head, and so your head moves a little bit longer than it does, than if it were to just hit the concrete. And so, but your head has the same change of momentum regardless. You're moving, and then your head comes to a stop because it hits the concrete. Okay? So delta P is the same in both cases. So that means this side has got to be the same in both cases. But what you want to do to reduce the damage to your brain is reduce this net force. You reduce that net force by increasing the time interval, right? So when you fall and hit your head, if your head comes to a stop over a longer time interval because you got some cushion there, you increase delta T, you reduce the average force, and thereby saving you some brain damage or some death, right? So you gotta wear helmets, guys. Wear helmets. This is why football pads work, right? If you have two 300-pound football players running at each other and they just collide, right? Without the pads, delta T is much smaller, which means the force that they experience would be much larger. If I was to jump off the top of this demo table and land on concrete, or jump off and land on a nice grassy grass, my feet are going to hurt less on the grass because the grass is going to give a little bit. The dirt underneath it, the soil is going to give a little bit. Again, it seems like when you just watch it, it happens real fast either way. But if you watch it in slow motion, it takes significantly longer, by fractions of a second, to come to a stop jumping on grass than it does to jump on concrete. So you can control the amount of force given the same change of momentum by controlling the time interval over which that force actually acts. Because this is so useful, notice it's called the impulse momentum theorem. This is change in momentum, obviously. This right here, the product of the net force on an object and the time interval over which that force acts is called the impulse. Again, the expression came first, and then the name, right? Force and time interval, product of that, it's very important. It's called the impulse. Right? Cool beans? All right. So, turns out that something that this is very useful for, I kind of alluded to it already, is the study of collisions. Study of collisions, and something that you might not expect to be almost exactly the same, at least as far as analysis goes, recoils. Like when you point a rifle and you pull the trigger, the bullet goes forward, the rifle goes backward. Right? Analyzing that, the physics of that, very similar to analyzing the physics of car crashes. We use the same general principles, the same starting point, actually. And in collisions, you obviously have forces, and those forces will act over time intervals. There's no such thing as an instantaneous force. Yes, if you're driving 60 miles an hour and you hit a brick wall, it's going to seem like that's an instantaneous stop. But if you use a high-speed camera and you slow time way down, you know that collision is actually going to take some amount of time that's not zero. So, turns out that when you plot forces versus time, right? We plotted before forces versus displacements and saw that the area under that was work. Remember doing that stuff? I know it was years ago when you guys were just small children. But we plot force versus displacement, we can get interesting stuff. We plot force versus time, we can get some more interesting stuff. And I like pointing out, it's I don't know, maybe the worst sport, tennis. You guys know? I'm just kidding. Normally I would pull this up, a video up, but I just ran out of time this morning and didn't have time. But have you ever watched a tennis ball get hit by a tennis racket in slow motion, super slow motion? It's very interesting. Like here, let's do a side view of a tennis racket. Here's the tennis racket. Here's the handle. So it's from the side. So before it gets hit, we say that let's just say that the ball, this is right before it gets hit. The ball is moving this way with some speed v. And just for the sake of simplicity, let's say that we got the tennis racket just held there by some arm that's holding it nice and tight. and we just shoot a tennis ball at it out of like a launcher, right? We just shoot the tennis ball this way. Well, it turns out that when that ball makes contact, the initial point of contact, it's not like, and it looks like it when you just watch it. It looks like it's instantaneous. The ball's going this way, it gets hit, it's going that way, like that, right? But if you slow it down, you actually see, like this would be, the strings actually will bend backwards. I'm exaggerating it here, but the strings bend backwards. And the ball, not only that, but the ball actually flattens out. The ball flattens out a little bit. And you can think of this as storing potential energy, storing elastic potential energy just like a spring, right? The strings stretch back. When they get stretched, they store some potential energy. And then the ball itself gets squished and wants to spring back, so it stores some potential energy, some elastic potential energy. Not only that, but you're swinging the racket, like not in this case, but when you're actually playing tennis, you're swinging the racket, so you get that additional force onto the ball. But going from here to here, the force will actually increase, right, on this time interval. So if I was actually plotting the force on the tennis ball versus time, it would start at 0, obviously, the instant right before, and I'm talking instantaneously right before, the instant before the ball makes contact, and then it will climb. And it won't be linear, it'll be something like this, until it reaches some maximum force where the strings have been fully extended, as much as they will. And then it starts springing forward, right? And notice though, the farther it's stretched, the farther the farther the strings are stretched, and the more squished the ball is, the larger the force is going to be, right? Just like when you stretch something against a spring. The farther you stretch it, the bigger the force gets. So that's why it's kind of linear here, because it's acting kind of like a spring. And then it reaches the maximum amount, and then it starts moving forward, right? And as it moves forward, the strings kind of start relaxing a little bit because they're moving back towards equilibrium. And so the force on the tennis ball starts to decrease, and then eventually reaches 0 at the point that the tennis ball actually is no longer in contact with the tennis racket. Does that make sense? Now, obviously, when you hit a tennis ball, this is a very short time interval, right? This is a fraction of a second, a small fraction of a second. But with modern technology, we can actually watch this happen. We can watch this happen. We can watch baseballs being hit by baseball bats. It's the same physics. When you hit a baseball with a baseball bat, the bat will flex. The bat will bend a little bit. The ball will squish a little bit. Yeah.
So how did they know this back then? They didn't have any of this technology.
Physics. Yeah.
So how did they experiment with that? I'm confused. I mean, they couldn't see that, obviously, so what? They said, oh, this ball...
Is probably assumed.
You can also slow
But
it
the
down.
physics works. I mean, the mathematics will work.
You can just make it bigger and slower and you still be able to see it.
Yeah. Yeah, probably. Yeah, there you go. Make a very large tennis racket with very, very relaxed strings, right? You don't tighten the strings too much.
Well, I don't know if you use 10. I mean,
The thing is that this is us being able to watch this. That's just the benefit of modern technology. This has been around since the 1600s. And so they were able to measure final velocities, initial velocities, masses, forces, time intervals. They've been able to do that since the 1600s. And so it's just we just get the benefit from modern technology to actually watch what's happening at a very slow pace. All right. Now, here's the deal. When we did, and let me just remind you, when we did work and energy, we learned that when we plot force versus displacement, as long as the force and the displacement are in the same direction, otherwise we got to deal with the cosine of the angle. But if we just plotted force versus displacement, and we had a constant force acting over a certain distance, this area equals the work done by that force. Why is that? Well, because work, I know, is force times displacement. Force is the height of this rectangle. Displacement is the width of that rectangle. So the force times displacement is literally just the area here. Even if the line was curved instead of straight. Okay? Same thing applies here, but force times time interval is not work. Force times time interval is impulse. So here, we can take our force versus time graph, and the area doesn't equal work, because for that to happen, it would have to be force versus displacement. That's the key. You take data, you put it on graphs. You learn how to analyze those graphs. You can get information from those graphs. Instead of plotting force versus displacement, I plot it versus time, and I see that the area is the impulse. Okay. And because I know by the impulse momentum theorem that the impulse is numerically equivalent to the change in momentum, then I know this area also equals the momentum change. And we'll do some example problems tomorrow, and then obviously you'll have an assignment where you do some of this stuff. You get a force versus time graph, you determine the area underneath it, and then you can set that area equal to either F delta T, or you can set it equal to delta P. So a question might give you an initial velocity and the mass of the object, and say here's a graph of force versus time. What's the final velocity of the object? Well, in that case, you'd set the area equal to delta P. And whenever you relate F delta T to the impulse, whenever you relate the graph of force versus time to impulse, usually if it's asking for a force, it's asking what the average force is. Because F delta T here, F is not constant in the case of a tennis ball being hit by a tennis racket. But what we could do is imagine in our heads, there's probably some force where if I was to graph it from the starting point to the ending point of the tennis ball being hit, where that area would be the same. The blue area here would be the same as the green area. There's some force where that would be true. And then we would just call that the average force. So if you have a question similar, or at least giving you a graph similar to the second page of the notes that you saw today, if you look on the second page. In this class, you don't learn how to find areas under curve graphs until you take calculus. You guys are doing that already? Mm-hmm. Okay. You don't learn how to do that until you take calculus. So if you see a graph where you have a changing force similar to this in AP Physics 1, it'll be more like that second graph that you see on the notes I gave you today, where you can actually find the areas there, right? Just by finding the areas of triangles and rectangles and trapezoids, if you remember that formula. Okay. So if a question were to give you that graph and say you can get the time interval just by reading the horizontal axis, so you set that area equal to F delta T, you can figure out what the net force was, but that would have to be the average force, right? Because the force is constantly changing on that graph. But again, even if you have a constantly changing force, we can compute the average force by just finding whatever force would actually give you the same area. And that's just as simple as taking the area of, those three triangles and that one rectangle, and then setting it equal to F delta T, dividing that area by delta T, and that'll be your average force. Yeah, we'll do some examples. We'll definitely do some examples. We'll do one example today and then a couple more tomorrow. All right. Now another thing, and I'll try to have this set up by tomorrow if I can find the stuff. I ran out of time looking this morning, but I don't know if I can find it anyway. Question that I usually pose. I don't have it to do this specific demonstration, but usually I'll take two balls. One of them's a bouncy ball. One of them is a lump of clay that's the same mass. And I'll make pendulums out of them. And I'll put identical blocks of wood in front of them. And I'll pull them both up and I'll let them go. The bouncy ball hits one block of wood and bounces off. The lump of clay hits the other block of wood and it doesn't bounce off. It kind of sticks to it, right? And the question before I do that is which one's more likely to follow? The one that gets hit by the bouncy ball or the one that gets hit by the lump of clay? A very similar question. Let's say I have a bouncy ball and a lump of clay that are both the same mass, and I'm going to throw them at this cupboard door at different times. I'm going to open this the same position, put the cupboard door at the same position, throw the lump of clay at the same spot on the cupboard door, and then do it again, but with the bouncy ball, throw it at the same spot with the same speed, at the same spot on the cupboard door. Which one of those is more likely to get the cupboard door to shut? Yeah, that's the question. What do you guys think? Does anyone have a yes? It's going to be the same. It's a valid. Not valid. That's a good answer.
You said they have the same mass?
Same mass. Same mass, same speed. Hitting the same point on the door.
It should be the bouncy ball, right?
Bouncy ball. Same. Bouncy ball.
The clay has a slower time, right?
Why?
Like a lot longer time.
Ooh.
Oh shoot.
Because the clay takes
That's not it though. That's not it.
That's not the reason?
No, that's not the total reason. But yes, no, that's true. That's true. Most people don't come up with that. I'll tell you right now, I don't know what's you guys just must be that sharp because most students end up saying, well, it's probably gonna be the clay. And when you ask them why, they say, well, the clay has momentum, and when it sticks, it gives the covered its momentum, right? Which is, it's not a terrible thought process. It's kind of intuitive.
I mean, this
However, this is a counterintuitive question because it is, in fact, the bouncy ball.
Because it gives more time, right?
No, less time.
The clay will have more time.
Less
The
time.
longer the time, the less the momentum.
Yeah.
Sorry, yeah.
The less the
Change in momentum.
The change of momentum for both objects will be the exact same, so you need the force to be greater, which means that the time needs to be reduced.
will the change of momentum be the same?
Change of momentum will be the same.
Let's clear up this mystery. Yes.
For both objects, because they have the same mass, the same velocity.
Same initial velocity. Do they have the same final velocity after the collision?
No.
No,
Oh.
because the basketball hits it more than once, right?
No, it just hits it
On a
once.
pendulum, yes, but
But the bouncy ball is going to have a larger, as we'll prove right now, a larger change in momentum than the clay would. And we're gonna use example 1 here to illustrate that fact. It's obviously a very different situation here, but it'll show the point. It'll demonstrate the point. Question? Okay. So example 1 says, look at the pictures below. If the raindrop and the hailstone have the same mass, which one of the two has a larger change in momentum? Justify your answer. So let's actually, I'm gonna add a little bit to this question just to drive the point home. So let's talk about the raindrop first. Now, one of the big parts of this unit is the analysis of collisions. Don't be jealous of my drawings, guys. And when we're analyzing collisions, this is where the diagram here is a little misleading. When we analyze collisions, we got to know what was happening the instant before the collision and the instant after the collision. And by instant, I mean the infinitesimally small moment before the collision and an infinitesimally small moment of time after the collision. What we want to know the speeds right before and right after of the objects. Okay. So if I was to draw that situation, I would say, all right, well, my raindrop has an initial velocity like this. Okay. And I'm going to use, I got to be careful here. Momentum, when we did energy, a lot of times the direction wasn't all that important because energy is a scalar, so we don't need to supply direction. Momentum is most definitely a vector. So I'm going to use, for both of these scenarios, my standard coordinate system. To the right, it's positive x. To the up, it's positive y. So if I was being very specific here, this vector is what? Positive or negative? Negative. So negative v naught. And then, the raindrop splats and stays. So what's its velocity afterwards?
0.
0. So the final velocity of the raindrop is 0. So let's calculate the change in momentum for that raindrop, delta P. Delta P is going to be mass times final velocity minus mass times initial velocity. What's my final velocity?
0.
0. And so my change in momentum is going to be negative mass times negative initial velocity. What's negative m times negative v naught?
Positive m v naught.
Positive m v naught. Notice change in momentum is positive. The change of momentum itself is a vector, and it is positive, which we expect, because what direction is the force going to be acting on the raindrop?
Say it one more time.
What direction is the force exerted by the car on the raindrop going to point? Up. So it needs to be positive. Well, look, the math tells us it's positive, right? And because I know that delta P needs to point the same direction as the net force according to the impulse momentum equation, we get what we expect, right? So that's the change of momentum. It's mv naught. So let's look at the hailstone then. And to drive the point home, I'm going to assume a perfectly bouncy collision here. Perfectly bouncy means that the hailstone is going to be moving up after the collision with the same speed it had when it was moving down right before the collision. If you had a perfectly bouncy ball, you would drop it and it would bounce, and then it would come back up to your height where you can actually grab hold of it. Right? We call those perfectly elastic collisions. How many perfectly elastic collisions do you think we encounter in nature? Zero. And remember, I've said this several times, but how many ideal gases do we have in nature? Zero. There's no such thing as a purely ideal gas. There's very close to an ideal gas, close enough that we can deal with it as if it was an ideal gas. Most gases are actually like that. But one of the assumptions that goes into, right, you make a series of assumptions to say that this is an ideal gas. You assume that the particle size is zero. You assume that, these are just two of them, I forget most of them. You assume zero particle size, which isn't true, but it's close enough that the size of gas atoms in comparison with the distances separating them is big enough, right? The mass is small enough, the particle size is small enough that you can assume they have zero size. And you also assume perfectly bouncy collisions. So you assume that no energy is lost, right? I drop a bouncy ball, if it makes it back to my hand, then it lost no energy in that process. And so that's a perfectly elastic collision. So that's just a little heads up as to where we're going tomorrow when we're actually going to start studying collisions. But when we're talking about the hailstone, the reason I brought that up is because I want to assume, just to drive the point home, I want you all to assume that the hailstone is like a bouncy ball and it's going to bounce up with the same speed it had when it came down. And then we can say, well, in the most realistic sense, it's going to have less velocity when it bounces up, but it's still going to bounce up. And so we can still come to the same conclusion. So again, initially I have the hailstone, same mass as the raindrop, with the same initial speed, which is negative V naught because it is pointing down. But then immediately after the collision with the rooftop of the car, it's moving upward with a final velocity of positive V naught. Right? I'm assuming that it's bouncing up with the same speed it had when it was right before. Again, it just makes the math turn out to be a little neater, and then we can come to a conclusion a little more readily, and then we can say, well, in the realistic case, when this speed is actually smaller, we get the same general idea, same general effect, but this just makes it a little more clear. So now I want to, again, compute the change of momentum. Again, it's just the final momentum, mv, minus initial momentum, mv naught. Well, my final momentum is v naught, or my final velocity is just v naught, and it's positive because it's pointing up. So it's going to be mv naught minus m times my initial velocity is negative v naught. Negative m times negative v naught is positive, so I get mv naught plus mv naught. So my change in momentum is what? 2 mv naught. And it is positive, right? Because again, what direction is the force that's acting on the hailstone as it hits the car? It's pointing up. So I end up with a positive change in momentum. And by the impulse momentum theorem, I know that whatever direction the change in momentum points, so does the net force. All right? So which one has a greater change in momentum? The hailstone does, the bouncy one. Now if our final velocity was smaller, this would still be larger than mv naught, right? So it's easy to see. If it's a perfectly bouncy collision, then I get exactly double the change in momentum. And this is where Kurt actually alluded to one of the major factors here. First of all, the change in momentum for the hailstone is twice as much, or at least significantly larger. So that translates to a larger force, right? Larger force on the hailstone than force on the raindrop. Also, delta T for the clay, it takes more time for the clay to, like clay or the raindrop to actually come to a stop, because it takes time to get squished, usually. you were to slow things down and actually count the time. So it's a smaller time interval or a larger time interval. You divide that change in momentum by a larger number, you just get a smaller force, right? Smaller net force. So first of all, larger change in momentum for the hailstone, and actually the hailstone will be in contact for a shorter amount of time than the raindrop. So you divide a larger number by a smaller number, and you get a significantly larger force. Now that is the force that's on the hailstone, or on the raindrop, or on the bouncy ball, or on the lump of clay, right? Whatever force is on the bouncy ball or on the lump of clay by Newton's third law has to be the same force that's on the cupboard door. So because we now know that the bouncy ball gets a much larger force, it's going to impart a much larger force onto the cupboard door. Larger change of momentum, larger impulse. Okay? And it's at that point I want to point out, you really want to get this down. This is linear momentum. We're talking linear momentum here, the momentum of objects moving in straight lines. Whenever I take an object that's moving in a straight line and it collides with something and then that something rotates, that's spinning momentum. That's not linear momentum. Does anyone know the technical word for spinning momentum? What's this? An angle? Angular momentum. Yeah. That's part of our rotation unit. Part of our rotation unit also, angular kinematics. The rotational equivalent of force. Does anyone know what that is? Torque. The rotational equivalent of energy, rotational kinetic energy. Rotational, not so much with rotational simple harmonic motion, but circular motion can be simple harmonic, as we showed in the last unit. And then we have angular momentum as well. Okay, so, yeah. It all boils down to this, though. But there are a multitude of different problems. Can you guys stop making noise, please, for a second? Till I'm done. We have several minutes. There are a multitude of different problems, different questions, different situations that you can analyze with the impulse momentum theorem. Okay. All right. Any questions? And if you want a heads up, you can read. This is an FRQ. Example 3 is an FRQ. I'm not going to say it's similar to the one that's going to be on your next test, but it is an FRQ from a former AP Physics 1 exam, an experimental design one. Okay, the test, I will... Oh, there's people that wanted to join? No, that's Physics C. The test will be graded, I'm hoping, by tomorrow. Again, if you bomb it after the curve gets applied, you can do the retake before the end of the week. If you do the retake, you must let me know. I still run into that. Students do retakes, and then they don't let me know. And I don't go into AP Classroom every day checking to see if someone did the retake. You have to let me know. Otherwise, it's not going to get graded, and Skyward's not going to get updated. This is the last week in the 6 weeks. I've had this student the last couple weeks, even though I've told... Not a couple weeks, but last week, at the end of last week. Don't come to me this week saying, what can I do to pass if you're not passing? What you could have done was done well on this last test. And stuff like that. What else?
Are you done grading our lab?
Yeah.
You are done grading our lab?
Oh, no. Am I done? No. No. I have a lot to catch up on. The labs are... Some of them are real good. A lot of those labs are no good, guys. A lot of those... I told you guys, complete sentences. People still not writing complete sentences. This is AP, guys. This is AP. It's not acceptable to... You can do bullet points if there's no punctuation in the bullet points and there's no periods at the end of sentences. Come on, guys. You're going to lose points for that. This is big kid physics. This is big kid writing. But yeah, I'll try to have those done. I'm trying to get everything updated in Skyward by tomorrow. Yeah. My focus will be on the test, though, so that you have time to make up the test if you need it. Yeah. Thanks again for coming in to get that test done this morning. I appreciate it. Whew. very bright today, Tatum.
Oh yeah, I decided to participate.
I forgot. I totally forgot. I have some neon stuff too that sucks. See ya.